Okay, so hi everyone, Senan this side, and in this video we are going to see how to detect a cycle in an undirected graph. So what you would be given is given an undirected graph with v vertices labeled from 0 to 1 and e edges. Check whether it contains any cycle or not. So graph is in the form of adjacency list, and adjacency of I would contain all the nodes. Ith node is having an edge. Okay, let's look at this test case. So vertices are 5, edges are 5, so there exists a cycle. We have the adjacency list corresponding to this graph, and the output should be true or 1. We are not asking, this question is basically not asking the path of the cycle, so we just need to detect it. Otherwise, if these 4 edges are 2 and you see this, you know that the graph is disconnected and there are no cycles, right? So we need to keep in mind that graph could be disconnected and graph may or may not contain a cycle. That is what we need to write the code for. Okay, so expected time and space complexity. Since we are using DFS traversal for this would be the expected time and space complexity for this algorithm. Now let's see what the algorithm is cycle is about. So since I'm using a DFS, I need to have a visited array to keep track of all the elements that I have seen till now, right? And for I is equal to 1 to v, for all the nodes, I would call this DFS if it is not being visited. So what this DFS would return? DFS would return if there is a cycle or not in this graph. And if that is true, we return true. Otherwise, we try for all the nodes, try DFS for all the nodes. And if we don't get a true at all, that means there are no cycles, right? So we just return false. Okay, let's look at this DFS function. And if you see the signature, you know that I passed the parent as well. Let's say I'm going through DFS. So I call for 0, then I go to 1. And from 1, I see I have 3 neighbors, 0, 2, and 4. And I can go back go back to 0 from this one. So in a way, I could detect that, yeah, there is a cycle. I went from 0 to 1 and 1 from 1 to 0. But that is not exactly a cycle. That is an edge. So we need to keep track that from which node did we came from in this child. The call from for DFS. We need to keep track of the parent basically. So that is why I have passed this parent as an argument. Now what I would do is, let's say I call DFS for this 0, then I go to 1, then I go to 2, then I go to 3, then I go to 4. And then from 4 I try to go to 1, but I see the 1 would be visited, since whenever I'm going through the DFS call I would mark them as visited. So 0, 1, 2, 3, 4 would be marked as visited. But from 4, when I tried to go to 1, that was visited, right? But I did not, it's not like that I went from 1 to 4 then 4 to 1. So the parent for 4 is 3 in this case, right? The way I'm trying to explain, the path that I took is from 3 to 4. So we were able to go to a visited node again, but not through its parent. That means there was another way from which I reached 1 again. So from 0 to 1 I reached 1, and from 3 to 4 and then 4 to 1 I again reached 1. So that means there must be a cycle along the way, and that is what we are trying to detect in this one. So this DFS would return true if there is a cycle. Clearly, when I start my DFS call from, let's say, I is equal to 0, I pass the parent as -1 because there are the vertices are labeled from 0 to v minus 1. So this is fine. So by -1 I just mean that there is no parent of this. Now let's look exactly how this DFS is implemented. The code is exactly the normal DFS solution, but with just this else if statement, right? And obviously we don't exactly have this return true or return false. So what this is doing, let's think about this recursively. So if I am at a node, so what I would do is I would first of all mark it as visited, and I would only call this DFS if that element is not visited, right? I won't be repeating the same DFS call. Now after that I try to find all the neighbors of this node, and I see if that node is not visited. So when that, so parent is also a part of this adjacency list, right? So for 1 we have 0 as parent as well, and as a child node as well. So for, since 0 would be visited already, we would be not going into this DFS call at all for the parent. But if visited, we have not visited that element, so there is a valid possible DFS call waiting for that node. What I do is I call this a DFS for this node, and what would be the parent? The parent would be this node that I passed in this DFS call. So that would be the parent. This would serve as the parent, and I just pass the visited array and the adjacency. Now let's say if this DFS call for the later, at some point we found a node, like in this case we found 4 went to 1, but 1 was visited and 1 was not the parent, so means that I detected a cycle, so I would return true in that case. In that case, this will return true, and it would go back the recursion tree till the time we go to this base DFS call, and if this is true, we return true. But let's say if DFS, so if I have already visited that element and that element is not the parent, that means I found another way to reach this element, right? I found another way to reach this element, and which is not directly the parent. So in that case, I have found a different way to reach that node, so there is a cycle. So in that case as well, I return true. Otherwise, I tried everything. I called DFS for all the nodes and I never got a true. So that means there is no node, or there is no cycle in that tree. So that is the whole video about. If you see, this is the basic DFS call. The worst case would be the max DFS call would be the number of nodes that are there. So in that case, the time complexity would be V, but at the same time you visit all the edges as well. For each node you visit all the edges, and you perform some actions, right? But you do check for every edge twice, right? For in this case for 0, or let's say for 2, I checked for 1 and 3, but for 1 I checked for 2, and for 3 I also checked for this 2. So these two edges are considered twice. So rather than V plus E, the time complexity would be V plus 2E, and the space complexity would be big of V, because at max that would be V DFS calls in the recursion stack space, and also big O of V for this visited array. We are not considering the space taken by the adjacency list. Hope that was clear, and hope you enjoyed this video. If you did, you can share this video with anyone you think might find this video helpful. But anyways, thanks for watching, and bye.